Okay, welcome back. I'm back at it again, trying to solve another Harvard physics problem. I mean, at least we're getting some variety now, because all the previous problems have been dealing with ropes. Now we're moving on to something a little bit more exciting, such as chains. And I feel like I could solve this one, because I was looking back at the other video that I did yesterday and saw what went wrong, what I did wrong, well, what I believe I did wrong. And it says a chain of uniform mass density per unit length hangs between two given points on two walls. Aside from an arbitrary additive constant, the function describing the shape should contain only one unknown constant. When I see this, when I see besides the additive constant, that obviously means we're going to do some integration. I mean, that's everyone's famous missed answer in the calculus problem, the plus c, you know? When in doubt, plus c. Okay, let's define the mass density. I'm going to define it as rho. I'm gonna use what I did yesterday and take an element of the rope, the thin rope, and define it in terms of infinitesimal stuff. I feel like I could solve this one because it seems like the same procedure as yesterday. What I'm gonna do is essentially define these points. I guess another thing to note is define this point right here. That's the point at the lowest point of the Hagen chain, meaning the slope is practically zero. I think that's a crucial point. The next thing we could do is apply Newton's second law. We're gonna have a weight go down, so it's a small weight. We'll have some tension force, P, and some tension force over here, P plus dP. And all this equals zero because we're at equilibrium. The rope is not moving with respect to time. I think I'm gonna just start with this equation and see what happens. So the trick here, I think, is that the angle theta changes along the path of the rope. So what I have to do is relate dl to d theta. So what I'm thinking is if we have a small element dl, there's going to be a small element d theta right there. And this is going to be dy and dx. I mean, that technically doesn't help me, but there is a trick. I mean, it's not really a trick. You're given it in this picture. We could say dy dx is just a tangent of theta. I mean, I guess that doesn't help that much. I mean, there's also a trig identity that I remember, so this is actually secant theta dx. I mean, I guess that doesn't... Wait, why am I doing that? Oh, shit. I don't even think I have to do force analysis on this, to be honest. I don't know why. Well, I mean, it gives you the mass per unit length. Because this just gives me the force. I realize I did that wrong, by the way. This should be tangent. Maybe you have to do a line integral? Oh, that's going to be a tough one, because I don't know how to do line integrals. Oh, God. To be honest, I thought I had this one. I was like, I finally have one that I could possibly do, and I realize I can't. So, I'm gonna think for a bit, and I'll be right back. I'm not gonna check the answer, by the way. I'm just gonna need some time to think. Okay, with some thinking, what I came up with is that if we need a position or the shape of the rope, we need both x and y. So that means you have to do a double integral, I believe. Huh. So I guess it doesn't really change the equation if I look at the vertical component. Wait a second. I think I thought of something. So if we have this equation right here, so we're trying to integrate this. So how does dl change with respect to x? Yeah, let's just rewrite. I realize these are the same equation, so these will just cancel each other out. I don't know why I did that. I mean, that's just a trig identity. That's what I used earlier. That didn't help me at all, but that's pretty cool that you could derive that trig identity from using that, basically. I mean, I guess they all come from right triangles, so it's not that surprising. This should be an easy problem. Like, it sounded very simple when I read the question, but now it's just like fucking hard as shit. So wait, hold on a second. I think I got it. So what that means is that the length of the rope over here is technically, we could use that as a determining factor when it comes to the weight. So we could take it proportionally to the length of the rope. basically from the point where the slope of the rope is 0, this will be length 2. So this is 0 to L2. So our axis curves with the chain. We could say that the weight of the rope is dependent on the positions. The total weight of this side of the rope, so W2, would be L over 2 over big L times the total weight. So our variable here is L. I feel like I'm gonna give up because I'm exhausted at like all the ideas I could come up with. This one was fairly creative. It was just, it's not working as planned. I feel like this might be the route though, because it relates the weight to position. So we get this. Oh, but we still have this variable here. Yeah, I am completely stuck. I don't know how to solve this problem at all. I think I'm done. I believe it's been almost an hour and a half. I don't really want to spend more time on this because I feel like it's very simple. Okay, I think I'm just gonna look at the solution. So here's the solution. The hanging chain will present 4 solutions. There's 4 different ways. Well, it says the first one involves balancing forces. That's the one I'm interested in. The other 3 involve various variations of a variational argument. What does that even mean? So they did split it up into horizontal component. So I guess he assumed a small angle approximation, and then you solve these differential equations. Then they use the Taylor series to approximate, which is basically what I was doing. That's the P plus dP, but they plus TdX times dx. So this is just a Taylor series approximation, first order approximation. I'm losing it here. I probably wouldn't have gone this far though. I probably would have got stuck here with a variational argument. I don't even know what that is. Oh, they used the minimized potential energy. What is that thing called? The Lagrangian? I'm not even sure how to use the Lagrangian. I never really learned it. I know of it, but I never really learned it. Yeah, I thought this problem would be a lot easier, but I am 0 for 3. I guess with that being said, I'll see you next time.